In the previous lesson, we looked at what polygons are. In this lesson, we shall consider the types of polygons. By the end of this lesson, you will be able to classify polygons as convex or concave, and also you'll be able to classify polygons as regular or irregular polygons. Polygons are classified according to the size of the interior angle and the length of its sides. And the size of the interior angles, we have the convex polygon and the concave polygon. Under the length of its sides, we have the regular polygons and the irregular polygons. We shall look at the properties of each of these types of polygons. So let's consider the properties of convex polygons, concave polygons, regular polygons, and irregular polygons. Now let's first look at the properties of convex and concave polygons. What makes the difference between convex and concave polygons is the size of the interior angle. Let's consider these two polygons. We have pentagon. Let's get another one. Hexagon. Hexagon has 6 sides. Hexagon. Now let's look at the interior angle of each of these polygons. We have the interior angle between the angle AED is 80.54 degrees. Angle between line DE and DC is 121.74. This angle is 101.61. 121.79. Let's also look at the interior angle for this. Okay. So from these two polygons, we have pentagon and we have hexagon. This is a regular hexagon. Now, if you look carefully at the interior angle for both pentagons, you realize that the interior angles, none of them is up to 180. This angle is 121.74, and then I think this is the highest. The highest angle here is 121.79 degrees. Now none of these interior angles here is 180 or more. The same thing applies to the hexagon. And when the interior angle of a polygon is when all the interior angles, the emphasis here is when all the interior angles of a polygon is less than 180 degrees, such polygon is convex polygon. So in this case, we have all the angles being less than 180 degrees, and therefore this pentagon is a convex polygon or convex pentagon. The same thing applies to the regular hexagon. Each interior angle is less than 180 degrees. Now, one thing that we should also look at is that for convex polygons, all the vertices are pointing outside the center. Now, the center of this polygon will be here, and all the vertices are pointing away from the center. The same thing applies to the regular hexagon. All the vertices are pointing away from the center. Again, another property of convex polygon is that all the diagonals will lie within the interior of the polygon. No part of the diagonal will lie outside the polygon. And the diagonal here is a line segment that connects two non-consecutive vertices of a polygon. So let's try. We have the diagonal from B to E. The diagonal is line segment which connects two non-consecutive vertices, and these points are consecutive, so it ceases to be. From here to here is not a diagonal. The diagonal will be from here to here. You can also have a diagonal from here to point C, diagonal from A to C, a diagonal from A to D. Now, none of these diagonals is having its parts outside a polygon. All the diagonals lies within the interior of the polygon, and so this is one property of a convex polygon. The same thing can be applied to the hexagon. Diagonal from here to here, from here to here, from here to here, from here to this point, from this point to that. And so all the diagonals of these polygons are lying inside the polygon. So for convex polygons, none of the interior angle is up to 180. Again, all the vertices are pointing away from the center, and it has all the diagonals lying within the polygon. Now let's look at properties of concave polygons. For concave polygons, it has at least one of its interior angle to be 180 degrees or more than 180 degrees. The emphasis is at least one of the interior angle being 180 or more. So let's measure the angles. This is 48.02. Okay, so we have all the interior angle here. The angle here is 48.02. Angle here is 110.16. This is 106.13. This is 53.62. However, the angle at point Q is 222.07 degrees, which is more than 180 degrees. And so this polygon how many? 1, 2, 3, 4, 5. This pentagon is a concave pentagon. Why? Because it has one of its angle being more than 180 degrees. Now the same polygon, if we can also turn it to a convex polygon. Now you see that none of the angles, the interior angle is 180 degrees or more. So this pentagon is now a convex pentagon. But when we alter the angle such that one of them becomes more than 180 or more than 180 degrees, then the polygon ceases to be convex, but rather it becomes concave. We can also alter this side, this angle. So you can make it this way. You can also consider other polygons. The heptagon, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. Oh, this is also a pentagon. This also a polygon. Now this is having 1, 2, 3, 4, 5, 6 sides. So this hexagon. Let's look at the size of the interior angles. Now you realize that the interior angle at W is 127, here is 108, 118, 46, and here is 52. But the angle, the interior angle at point S is 266.53, and therefore, because this angle alone is more than 180 degrees, this polygon becomes a concave polygon. We can also alter this. So that this also have an interior angle of 253. The emphasis is if at least one of the interior angle is more than 180 degrees, then such polygons are concave polygon. Now let's look at the diagonals. Now the diagonals of a concave polygon, at least one of them has part of it be falling outside the polygon, or all of the entire polygon, the entire diagonal falling outside the polygon. Let's look at the diagonals. The diagonal from this point to this point, it lies within the polygon. Diagonal from M to O also lies within the polygon. However, diagonal from O, this is a consecutive point, so O to Q lies outside. In the same way, for this hexagon, Diagonal from R to T lies outside. Diagonal from T to V lies within. Diagonal from T to W lies within. But diagonal from so lies within. But diagonal from U to W will lie outside the polygon. So another property of concave polygon is that at least one of its diagonals lies outside the polygon. So for concave polygons, at least one of the interior angle is more than 180 degrees, and also at least one of its diagonals falls outside the polygon. Now if you notice, you realize that the vertices of the concave polygon, at least one of them is pointing toward the center of the polygon. So in this case, all this point M, point Q, point N, point O are pointing away from the center. However, point P is pointing toward the center of the polygon. The same way, point R, point W, point U, point T of this polygon are pointing away from the center, but point S and point V are pointing toward the center of the polygon. Now let's look at the properties of regular and irregular polygons. The regular polygon regular polygon of 5 sides. Pentagon, regular polygons of 6. Okay, let's measure the size. Now the difference between regular and irregular polygon also lies between the size of its sides, that is the length of the sides. So here we have regular quadrilateral, we have regular pentagon, regular hexagon, and regular heptagon. Now we're going to look at the sides. Let's measure the size. This 1.93. Good. So this is a square and it's a regular polygon because all the sides are 1.93 centimeters. The same thing. Now let's look at the pentagon. Is 1.94. So we realize that all the sides are equal in length. 1.87, 1.87, 1.87. Yes. 1.41, 1.41, 1.41. So one thing that we've realized is that this is a regular polygon. Why? Because all of them are having the sides to be the same in length. For the square, the length is 1.93 and it's the same for all the sides. We have pentagon having each side to be 1.94, then hexagon having each side to be 1.87, heptagon is also having the size to be 1.41 for all the sides. So for us to consider polygon to be regular, then all the sides should be the same in terms of length. Let's also look at the angles, the interior angle, the angle between this and that. We have 90. This is having all the angles to be 90. Let's look at this. Now for the regular pentagon too, it is having all the interior angles to be 108 degrees, and put the angles at the corner. Angles at the corner. So we see that all the interior angles for the pentagon, the regular pentagon, are also the same in size. Let's see, check for the hexagon. Now for the hexagon, all the interior angles are also the same, and that is 120. So this suggests that for a regular polygon, all the sides are the same in length, and all the interior angles too are the same in size. Let's try by looking at the length. If you change the length, that the interior angles change. And this is a pentagon. We have increased increasing the sides of the pentagon, and you realize that as we increase the sides, all the sides are 5.4 centimeters, 5.4 centimeters, or 5.4 units. Good, 5.4 units. As we increase the size, the interior angles remains the same, and they are equal in size as well. So no matter how you change the length of regular polygons, the interior angles remains the same. Okay, so let's also look at the hexagon. You realize that as we change the length, now the length is now 3.141 units, but the interior angles remains 120. As we change, now the length is 3.85, but the interior angle is unaltered. The size is now 4.8 units, and the interior angles are the same. Okay, so for regular polygons, it has length, it has its size to be the same in length, and also the interior angles are also the same in size. And let's look at the irregular polygons. Irregular polygons. Now for the regular polygons, they are the same in size, that the interior angles are the same in size, and the sides are also equal in length. And the opposite is true for irregular polygons. Let's look at irregular polygons. This is a quadrilateral. Let's also draw another polygon, pentagon. 5. Another one. That's hexagon. Hexagon. 1, 2, 3, 4, 5, 6. Now let's measure the length of each side. This is 6.43 units, 4.23 units. Okay, it's 2.15. So you notice that the sides of irregular polygon are not the same in length. The sides of irregular polygons are not the same in length as compared to that of the regular polygons. Now for the regular polygons, we realize that they were the same in length, the sides are the same in length, and the interior angles are also the same in size. Now for irregular polygons, we've seen that the sides are not the same in length. Let's also check for the interior angles. Okay. Now you realize that from this figure, all the interior angles are not the same. They differ from one another. And so for irregular polygons, the sides are not the same in length, and the interior angles are also not the same in size. But for regular polygons, the sides are the same in length, and the interior angles are also the same. But for irregular polygons, the sides are not the same in length. At the same time, the interior angles are not the same in size. Therefore, in this lesson, we learned that polygons can be classified according to the size of the interior angle and also the length of its sides. Under the size of the interior angles, we have convex polygons and concave polygons. For convex polygons, all the interior angles are less than 180 degrees. All the vertices point away from the center. Also, all the diagonal lie within the interior of the polygon. For concave polygons, at least one of the interior angles is greater than 180 degrees. At least one of the vectors points toward the center of the polygon. Also, at least one of the diagonal lie outside the interior of the polygon. Under the length of each side, we have the regular polygon and irregular polygons. For regular polygons, all the sides are equal in length, and all the interior angles are equal in size. For irregular polygons, all the sides are not the same in length. The interior angles are also not the same in size. Subscribe to the YouTube channel and click on the bell for prompt notification anytime a new video is uploaded. Thank you for watching.